All right, so the next thing we want to talk about for ATS testing is I want to give an example of cable testing, right? So when you are cable testing, a lot of times it's going to be new cable or it might be old or aged cable, but regardless of the cable type, the manufacturers and these types of cable, they're generally all tested about the same, but their test values could vary widely. And so we're going to do an ATS example. And in this ATS, I'm going to scroll down and we're going to get to cables. Okay, so cables is going to be right here, medium voltage cables. And we're going to click on it, page 43. We're going to go to it. So here we are on page 43 looking at the medium voltage cables. And it says in here under the electrical tests, and I'm going to hone in specifically on one test. I'm not going to go through all the stuff on cables, but it says perform an insulation resistance test individually on each conductor. And what we're trying to do is we're trying to test the insulation of or test the resistance, the insulation resistance of the insulation itself. Okay. And so in the absence of manufacturer data, use this table. Now, let's be honest. A lot of people out there will say, look, if it tests greater than this, cool. If not, I'm not going to do anything. I'm not going to look anything up. Okay. Most of the time, that's generally acceptable. But what's going to get you is those times when it's below this number and it's probably still good. So I'm going to go to this table and what we're using here for this example is something that I've run into before, and I just want to kind of showcase it, how we got through it. So we were testing 35 kV, and this was EPR cable, and it was, it's LS Cable is who makes it. It's 35 kV, MV105 is the spec, and what we were testing was 750s. They are big cables. So, or at least pretty good size. So that's the cables that we're testing. So most people are going to say, hey, 100.1, cool. So here we are at table 100.1, and I'm going to zoom in just a little bit. So this is a notes section. I'll go back out. You see how this is notes. This is going to be important. We're going to look at this here in a second. Okay. So we're testing these cables, and these are 35 kV cables. So we're here. We're going to test them at a minimum DC test voltage of 5 kV, and 5 kV is really nothing for this cable. Okay, 35 kV divided by 1.732 is 20 kV. It's actually 20.2. So that's the phase to ground voltage of that cable. So you could probably get away with 10 kV or even a 20 kV test if you really wanted to. But so regardless of which voltage you use, it's 100 mega ohms or 100, I'm sorry, 100,000 mega ohms or 100 giga ohms is your expected result. Okay, so the problem that you're going to run into with this is that a lot of times on these much bigger cables, some manufacturers don't get anywhere near that. Okay, and if you read the note down here, for medium voltage cables, the values shown are typical conductor and insulation, geometry, temperature, length of the cable, all need to be taken into effect. The older NETA tables, this is something you won't get out of this book. The older NETA tables used to say per 1,000 foot. Okay, so we don't have that shown here, but you just have to kind of put that in the back of your mind that it's expected to be 100 giga ohms per 1,000 foot. So if you have 2,000 foot of cable, it's 50 giga ohms. If it's 3,000, it's 33 giga ohms. Okay, you just divide it by how many thousands of feet you have. So this is what it says, but when we were testing out there, we got numbers way lower than that. We got numbers in 50 giga ohms, and we were like, wow, this is not anywhere near passing. And so we started looking at the manufacturer spec, and we are like, okay, well, we need to actually look at the manufacturer spec. So here is the manufacturer's cable identification, part number, and everything right here. And then here's the dimensions. This is a very important table that we're going to need here in a second. So if you really dig into the manufacturer's literature, you can find this. And every single manufacturer has this. You just have to look for it, okay? We were testing EPR cable, and it was graded greater than 2 kV. And so in order to perform the actual calculation, what you do is let's zoom in on this a little bit and I'll show you. You have to go ahead and there we go. It's going to be this calculation right here. So IR equals K times log base 10 of D divided by D. Now D, it tells you what everything is right here, okay? This is going to be the insulation resistance in mega ohms per 1,000 feet at 60 degrees Fahrenheit, which is 20 Celsius roughly. Okay, so it's telling you exactly what we're really looking at. Okay, it's actually 15.6 Celsius, but no one's counting right now. So we have K is going to be some kind of, offset factor depending on what type of cable you have. And then you have your inside outside diameters. Everything else, log is a function like sine. Okay, so let's go to the other sheet. We have right here our inside and outside cable diameter. Now I told you it was 750s, okay? It was aluminum cable. The outside diameter is the insulation diameter, okay? That's the outside diameter of the sheet of the insulation. And so when we look at this picture right here, we're talking about the distance from right here, okay? I'm going to draw a line kind of like pointing from this distance right here to this distance right here, okay? So we're really looking at, I'm going to draw a rectangle over it. This is the total distance right here, the right side of this rectangle. That's the distance we're looking for, okay? And so that's the outside diameter divided by the inside diameter. The inside diameter is, if you look at the picture, it's your conductor. The outside diameter is the diameter of the insulation. So we can look right here on this sheet and we have outside diameter 1.69, inside diameter is 0.968. Our K value, right, that we had EPR and it was high voltage rated at greater than 2 kV. So our K value is 20,000. We have everything we need. So I have another thing pulled up over here to go through it. So we have K equals, this is our base equation right here, and our ohmic value per 1,000 feet. Our K equals 20,000 ohms. D, big D and little d right here. And then we're going to divide them out. Big D divided by little d is 1.69 inches divided by 0.968 inches. Divided out, you get the inches will cancel out of each, right? You're dividing inches by inches. So it's just a ratio or a number now, 1.746. Put that into a log and you find out that the log base 10 of 1.746 is 0.242. So you multiply that by your 20,000 ohms, and what you get is this cable should have been testing at 4,800 ohms, mega ohms. This should be meg right here, mega ohms per 1,000 feet. So our numbers were well above that. We had like 3,000 foot of cable or something like that, but it was well above, maybe it was 2,000, I can't remember, but it was well above what we were getting. So if you have 3,500 foot of cable, you would take this number, and that's 1,000 divided by 3,000, whatever your cable length is, right? So 3,560. And I'm going to do that on my calculator right here in front of me. 1,000 divided by 3,560, and you get 0.28. And then you multiply that by this number, and that gives you your new number. And so if we had cable this long, we had cable that was 3,560 foot long, our ohmic value should be somewhere around 1,359 mega ohms, or 1.359 per conductor. So per run. So if you have 5 parallel sets or whatever you have and you're testing them all at the same time, you can compensate and make them parallel, and then you can figure out exactly what your ohmic value should be. So this is something that is not widely used. I think that it needs to be employed a whole lot more, and people need to start understanding how to do the math to actually assess whether or not they have passing cable. Okay, because this was brand new cable straight off the reel, and it tested way better than the manufacturer specifications did, but it failed the NETA table, and that's what got everyone all riled up. Okay, so The NETA table is not gold, it's just a guideline. What is gold, what NETA is going to tell you to follow, is the manufacturer specification, and that right here is how you follow it for medium voltage cable. So hopefully this helps.